Bismillahirrahmanirrahim. Our today lecture is about irrigation canals, and in this chapter we will study the canal design, sediment transport in the canals. For canal design, the most important thing is that a canal should be non-silting and non-scouring. There should be no siltation, no sedimentation in the canal, and there should be no scouring, no erosion from the bed or the banks. So, whenever we have precipitation in the catchments, in the upper catchments, like catchments of Indus river, like areas of Gilgit, Hunza, Nowshera, Kabul and etc., then soil erosion occurs and the sediment enters into the river. Whenever we offtake a canal from the river or dam, then our main target at canal intake is always that a canal should offtake the maximum possible silt-free water. Simply we can say there should be minimum entry of silt into the canals, and this is the main reason that why we stop canal operations during floods due to heavy sedimentation. And if those sediments enter into the canals, then those sediments can reduce the discharge carrying capacity of the canals. So we cannot stop completely the silt entry into the canals, but we can minimize the silt entry into the canal at barrages or dam. So when silt enters into any main canal, like any of the main canal, like Lower Chenab Canal, then this silt should be transferred from main canal into branch canal, then from branch canal into major distributary, then from major distributary into minor distributary, and then from minor distributary into the water course through the outlet. So our target is that when silt enters into the canal, it should be distributed up to the farmer's field. If the silt is not transferred to the farmer field, then with the passage of time, the discharge carrying capacity of canal network, like main canal, then major distributary, then minor distributary, then water course. After main canal, there is branch canal, then major distributary, minor distributary and water course. So the discharge carrying capacity of these irrigation network can be reduced. So this is the main target, that sediment transport study is very necessary in case of canal designing. And we will use the equations of open channel here. And the sequence is that from barrage we offtake main canal, and main canal divert water to the branch canal diverts to the major distributary, and major distributary diverts to multiple minor distributaries, and minor distributaries divert water to the water course from outlet. We studied in our previous lectures, chapter 8, outlets. So irrigation canals are of two types, lined or unlined canals, and canals are of two types, lined canal and unlined canal, and lining is not possible everywhere, so design of unlined canal is very necessary. Then we can use these two equations, Manning equation. I think you will be very well familiar with these two equations in FPS system and system international units. And this is the Chase's equation, CRS under root, velocity, hydraulic mean radius, area, batted perimeter, slope, Manning coefficient and Chase's coefficient. And the section factor, which is a raised to power 2 by 3, this factor is known as section factor in case of Manning equation, and it is, and in case of Chassis equation it is this ar raised to power 1 by 2. And discharge in uniform flow is a function of this and longitudinal slope. And the best hydraulic section, we also know that, which has minimum wetted perimeter, and this will give maximum discharge for the given area, and Q will be directly proportional to a raised to power a divided by p raised to power 2 by 3. And one thing more, that it is not necessary to remember all the equations. You should be well familiar with the equations like Manning equation, Chassis equation, area calculation of trapezoidal channel, rectangular channel, wetted perimeter of trapezoidal and rectangular channel. These some of the basic equations. So for the best hydraulic section, we usually design trapezoidal channel. Area should be 1.73 y square, wetted perimeter should be 3.46 y, and hydraulic mean radius, it should be 0.50 y, top width and depth. But we will design the canals as per given criteria. Then a freeboard should be added. It is a vertical distance between the maximum water level and top of the canal bank. It is provided for seasonal fluctuation in the water, and its equation is F is equal to Cy under root. C is the coefficient, which varies from 1.5 at 20 cubic and 2.5 at 3000 cubic. You can interpolate from 1.5 to 2.5, from 20 to 3000 cubic. And Y is the depth of water in feet. And sometime we have curvature in canals. Then it is very necessary to understand the water level difference between both the sides. For example, if a canal has curvature, then there is a rise of water on the outer side due to velocity, due to higher velocity on the outer side and lower velocities on the inner side, and that affects the freeboard. And if we want to know the change in water surface elevation, this equation can work. Here V is the subcritical average velocity, R is the distance from center of the curve to the center line of the channel, and H is the change in water surface, B is the width of the channel. And this effect of curve is negligible when we have large curve. When we have large curve, when the ratio of radius of curvature to the distance to the center of the canal, when ratio of radius of curvature to the distance to the center of canal is greater than 3 times the bed width of the channel. If radius of curvature, which is from center of the canal, if that is greater than 3 times the bed width, then we can say there is no effect of curvature, and we do not need this equation in those cases. So in case of unlined channel, curvature assumes a greater significance due to siltation on inner side and scouring on the outer periphery due to higher velocities on outer side. And in Pakistan, where most of the irrigation canal are unlined, the practice recommends a minimum radius of 300 feet. So radius of curvature should be more than 300 feet for canal carrying less than 10 cubic, and 5000 feet for canal carrying more than 3000 cubic. So our main canals in Pakistan are usually more than 3000 cubic, so their radius of curvature should be 5000 feet, about 1 mile. And for design of line canal, what are the procedures? So we have to estimate N or C for the given lining material first of all. Then we have to compute the section factor. If we will have N, we will have Q, S and theta. And theta is basically a factor which is used in Manning equation, 1.49 in FPS and 1 in metric system. Then we have to assume the shape of the line section, trapezoidal, and its slope. Then we have to, for the best hydraulic section, we have to calculate the channel parameters, and then we have to check for minimum permissible velocity. Minimum permissible velocity is used if as a threshold. If the velocity will be less than minimum threshold, then siltation will occur. If a canal is carrying some sediments, then in our design, our target should be that those sediments should remain in suspension and should be transferred from one canal to the other canal and up to the watercourse and up to the farmer field. If the velocity will be less than minimum permissible velocity, then siltation will occur. So this is a case of lined canal. So in line canal, maximum velocity does not affect, because the canal is totally lined, and the factor is only minimum permissible velocity. Then we have to calculate the Froude number. It should be less than 1. So what is the concept of Froude number? If Froude number is less than 1, the flow is subcritical. So in our rivers and most of the design canal, we prefer the subcritical flow. If Froude number is equal to 1, then the flow is critical. If Froude number is greater than 1, then flow will be supercritical. So what is the main difference? In subcritical flow, we have less velocity, and the channel section or area will be more, or depth can be more. But in supercritical flow, the velocity is more, and which can affect the unlined canals, which can erode the particles from bed and banks of the canal. And then we have to estimate the freeboard. So this is the example 4.1. A line irrigation canal is to be designed to carry 1000 cubic. The concrete lining is smooth and general ground slope is 0.001. So for standard table of Manning equation, smooth concrete has an roughness coefficient of 0.015. And then section factor A r raised to power 2 by 3. We have N, we have Q, we have S. It is 314.4. Then we have to assume B and side slope. We can calculate depth, side slope. So when we enter these two values in this equation, then we can get Y is equal to 5 feet. And in second trial, we assume 30 feet width and same side slope, Z is equal to 2 for lined canal. And in this case, we can calculate Y as 4.5. So there is very minor difference in depth. At 3 feet we have 4.5, and at 20 feet we get depth 5 feet. So 20 feet bed width should be good in this case, and it is preferred. So we have to check for velocity. We have to calculate area using B into ZY, BY and ZY square. 150 square feet we have to enter into this equation. We can get the velocity 6.66 feet per second. So there is no limit on maximum permissible velocity in line canal, so it is okay. Froude number V over YG under root. G will be 32 point something, and Y is equal to 5 and V is equal to 6.6. We can get 0.523. Then flow is subcritical. Freeboard C is equal to 2, and 2 and 5 we can get 3.33 feet. So top of lining above the water surface is 50%. For example, freeboard is 3.33 feet, then it is not necessary to completely line the freeboard area. You have to line 50% of the freeboard area. Design of the unlined canals. The design of unlined canal is a greater challenge, and the design will remain stable. It is an important challenge to the researcher and designers. The solution of the problem consists in determining the main factors like depth, bed width, side slope, longitudinal slope of the channel, as to produce non-silting and non-scouring velocity for the given discharge and sediment load. So there are few empirical approach with respect to time. Different researchers perform different experiments even in Pakistan, in Indus Basin, and on those bases there are some canal designs like Kennedy silt theory, Lindley's modification, Wood's improvement, and Lacey regime theory. Then within the Lacey regime theory, Lacey shock theory, Blanch contribution, Simon and Albertson approach. So we will discuss now these approaches one by one, and then we will design on basis of some given numerical or data. So there is an empirical approach which is adopted by American Society of Civil Engineers in 1920, and results of survey were published. So on the basis of method of maximum permissible velocity, and in United States this remained as a tool for design, while rational approach was continuing to develop. Nowadays tractive force method and Lacy regime theory is working. There are other theories like Debye function, Einstein function, suspended load function, and we will study. So first of all, Kennedy-Silt theory. Kennedy was the first engineer to do research work on scientific basis, and he was executive engineer in Punjab irrigation in charge of Upper Bari Doab Canal in Pakistan. In 1895 he performed some experiments, and he selected 20 sites in the middle of the Upper Bari Doab Canal, and he found that a regime channel is one which neither silts nor covers. So first of all we will see what is a regime, we will discuss. Then the regime channel is one which neither silts nor covers. The eddies generated from the bed, from the channel bed, supports the silt in suspension, and therefore the silt supporting power of the stream is proportional to the bed width. If bed width is more, then this you can say its silt supporting power will be more, and it does not depend upon the perimeter of the channel. So the bed width is more important in case of silt supporting power. Then the critical velocity ratio, the critical velocity, which means non-silting, non-covering velocity V0, that is given by 0.84 into d mean depth of channel, and so we can see 0.84 is equal to C coefficient, and 0.64 is B, that is also coefficient. Then another factor M, which is critical velocity ratio, was introduced, that is equal to actual velocity over critical velocity, that is called as critical velocity ratio. So that is equal to M, and that is equal to V over V0. You can see this equation. Then sand, we can say if sand coarser than the standard silt at Upper Bari Doab Canal was assigned the value of M from 1.1 to 1.2. If there is sand, then we can assign higher values, and if there is silt, we can assign a little bit lower values. Then again we have Chase's equation, we have value equation of C to be incorporated into this. V is equal to CRS under root. In C we have value of N, we have value of S, and we have value of R. R mean hydraulic mean depth. So in Kennedy theory there was no relationship or ratio of B and D. There was a relationship of only velocity and depth. So the depth and bed width are not correlated in this theory. In this example, design a channel as per Kennedy theory to carry a discharge of 60 CFS cubic feet per second with longitudinal slope of 1 feet per canal mile. N is also given, M is also given, M is equal to 1. So velocity will be equal to critical velocity. So you have to enter this equation. D is equal to, we have to assume the depth at first. We have to assume depth, which is 2 feet. Then we have to use velocity equation. We have to enter the D and M. We can get 1.31 feet per second. We can calculate area. Discharge area is equal to discharge over velocity, 60 over 1.31. Area is 45.8 square feet. Then with side slope of, so this is unlined canal, we will prefer this side slope for unlined canal, 1/2:1. You can calculate, if we have area, we can calculate bed width. So you can check this equation using this CV is equal to CR under root. C, we have to enter N, we have to enter R, we have to enter S. So that is equal to 1 and hydraulic mean depth, which can be calculated as H is equal to A over T, area over top width. You can calculate hydraulic mean depth, and hydraulic mean depth you have to enter here. So you have to calculate it, area divided by top width, it will be resulted in 1.32. You have to find C, then you have to calculate V is equal to C R and S under root. Then you can calculate the velocity, which is equal to the previous calculated velocity at depth, is because we assume depth 2 feet. If that velocity and this velocity is different, if these two are different, then you have to re-assume the depth. And so this design is satisfactory. Then modification and improvement to Kennedy theory. The first modification was made by E.S. Lindley, and he introduced that V has direct relation to D, and velocity has direct relation to bed width, and bed width has direct relation to depth of the channel. And the second modification in the theory was made by F.W. Wood's equation, and he analyzed Lindley's data. He analyzed the data of E.S. Lindley, and he agreed with him that the stable channel carrying the sediment charge must have a fixed bed width, depth and slope. So he introduced depth and bed width relation, velocity and bed width relation, and slope versus discharge relation. And the third is Lacy regime theory. So for Lacy regime theory, we have to understand what is a regime. What is a regime channel? So for a regime channel, Lacy regime theory, there are three types of regime: true regime, initial regime, and final regime. So what is initial regime? A channel is in initial regime when the bed slope gets affected due to siltation and scouring. In the initial stages, the silting and scouring can occur. So this regime theory is not valid for initial regime. Second one is the true regime. A channel is in true regime condition if water transported and sediment are in equilibrium such that it is neither silting nor scouring. And there are conditions for true regime. If discharge is constant and flow is uniform, the amount of silt is constant, the size and type of silt are always the same. When a channel is flowing through a material that can be scoured easily, then such soil is known as incoherent alluvium like sandy soil. And the third one is final regime, when the parameters like slope, depth, all the other parameter, wetted perimeter, hydraulic mean depth, are varying as per the flow rate. If flow rate is varying, then these parameter can vary. If flow rate is constant, then this parameter can also constant. Then the grade of silt, then it is said to be in the final regime. And grade of silt mean silt grade, I mean to say its size basically. So there are three types of channel shapes. For example, this shape can occur when channel shape carrying fine silt, and the medium shape can occur carrying medium size silt, and when it contains coarse silt. So our rivers and canals are usually containing coarse silt, sandy soil, so their shapes are longer. In our rivers, bed width or top width is more and depth is less. So these are the equations we will study now. So Lacy published his paper through the Institution of Civil Engineer London in 1922. He made a systematic study and observed data and derived some empirical equations. So its concept was similar, that discharge is constant as we studied from the internet, and alluvium is incoherent, unlimited, and of same characteristics, and silt grade and charge are constant. Silt grade means size and charge mean sediment concentration. Obvious in ppm. All the above requirements are unlikely to be fulfilled in nature. So we can see divide in true regime, initial regime, and the final regime. So Lacy regime equations. These are the Lacy regime equation which he derived from Upper Baridwab Canal, Lower Chenab Canal, and Indian Canal, Madras Canal. And he introduced some equations like V is equal to KFR under root. So we will not go into deeply deriving these equations. We will just indicate the equations, and this other equation is equal to K is fixed and it is 1.1547 F into R under root, where F is Lacy's silt factor and R is hydraulic mean radius. For the standard condition Upper Baridwab Canal, he introduced K is equal to 1.1547 and silt factor is equal to 1. So its equation can be directly related with this, but he introduced the Lacy silt factor, which is directly proportional to m square, which is Kennedy critical velocity ratio. We have studied previously, and for the materials against Lacy silt factor, we can get the value of F. If it is, for example, coarse sand, its value is 1.31, medium sand, and if it is massive boulders, it is 39 point something. So we remain here in this range. We usually encounter coarse sandy soil, and there are further equations which are in Kennedy, which are in Lacy regime theory, like equation 4.12 and equation like this one 4.13. He derived equation 16 R2 by 3 S1 by 3. This equation is very useful for calculating flood discharge in rivers. So in rivers we can use these equations for large discharge, and is better than Manning-Urquhart's equation. The latter involves n. The Manning-Urquhart equation involves n Manning coefficient, which value has to be based on experience. And for channel not in perfect regime but in initial and final regime, Lacy derived the flow equations. So if a channel is not in perfect regime, it is initial or in final regime. If it is not in true regime, then he derived the equation, and you can use these equation like this equation 4.14, and we will use these equations in numerical. Equation 4.15 is also very important, which includes Manning n value. And Lacy equation for wetted perimeter, he derived for the separate equations by considering the special focus on wetted perimeter, and he correlated the velocity with P, he correlated velocity with R and A. And this equation is one of the main equation. And this equation 4.17, V is also function of discharge and F. Silt factor, wetted perimeter equation. This is the most common equation in FPS system. 2.67 into Q under root, and it is 4.75 into Q under root in system international unit. 2.67 in this FPS system. And range of values of plot, it should be from 5 to 3000, and velocity 1 to 4 feet per second. So limited range, since for river the mean velocity exceeds even 10 feet per second, and AF square may be the order of 10 or more. So this equation has been successfully checked against considerable data, nevertheless checked, and for artificial channels a slight variation was found of the order of 0.05 in the coefficient of 2.67. It may be plus and minus, but we can take these values of 2.67. So this is the most commonly used equation for wetted perimeter, for the velocity equation. And the last effort made is scour depth and regime slope discharge equation. So in this equation number is 4.20 is important, that is for hydraulic R, that is equation of R. And since equation 4.20 is the scour depth formula, so this is the scour depth formula for a regime channel. Scour depth formula means the maximum scouring depth which can occur in a river. Depth of flow is little bit another term, and scour depth is another term. For example, if depth of flow is 5 feet and scour depth R, we get R as 8 feet, then we can say the lower 3 feet from channel bed to the down below the bed 3 feet can be eroded. So R is the maximum scour depth, that the maximum scouring at the bed, how much depth this scouring can occur. And since for a wide channel the hydraulic mean depth is almost the depth, so equation 4.20 can be utilized for determining the depth of flow in a river during flood. Since a river in flood is temporarily in regime, this depth will be equal to the normal scour depth and will be measured from the high flood level, and will give the level of the scoured bed. means to say in flood the maximum covering which will occur, that will be counted as R. And further equations are like equation number 4.22, the equation of slope with F and Q, and equation of R with Q square and F. Small q mean that is discharge per unit river width, So in summary, these are the equations which we can use, which are under the Lacy regime theories. So these equations we can use in our practical example. Here N1 has equation 0.0225 F raised to power 1 by 4. And these are the name of the canal, and these are their completion year. And example 4.3, design an unlined channel as per Lacy theory to carry discharge of 60 cubic with a longitudinal slope of 1 feet per canal mile. The following equation can be used: velocity, slope, parameter and velocity, and there is another equation of velocity. So equation V is equal to 16.0 SR 1 by 3 R 2 by 3 is more appropriate for rivers than artificial channel, for which an equation involving N1 is more suitable. So we use first we can use the equation of this slope, that is equal to 1 over 5000 1 feet per canal mile, that is equal to F, and 60 here we can find F. We can find P by using value of Q in cubic. The P is 20.7 feet. Then we can use N1. We have F, we can find out N1 using this equation. And then after N1 we can use both the velocity equations, this one and this one, and both the equations will help to find out R and S, R and velocity. We will use these two equations of velocity, and we can get R, and from R we can calculate area is equal to PR, and side slope again 1 by 2 ratio 1. Then we can find out the other parameters like B, D and velocity. So there are further developments in Lacy regime theory. That first is Lacy shock theory. Data collected by canal engineers show on analysis that silt factor F, which is Lacy silt factor, instead of being constant, it varies with season and within one season in a single section of a canal. The value of F can be calculated, this equation again, and it was found that different from the value calculated from SQ equation, since coefficient of rigorosity N1 is a function of F, and above statement is true for N1. So Lacy later experienced this phenomena in shock theory. He divides this frictional resistance F. In previous studies it was simple F, and in Lacy shock theory Lacy divided F into two different components, and he divides friction resistance in two parts, one due to varying degree of grain surface of the soil particle, and other due to resistance offered by the irregularities of the bed and site, which offer I mean to say the resistance which is offered by the soil to the erosion or scouring. The second type of resistance is due to from drag, which is created by ripples in the bed. So what are the ripples in the bed? There are irregular bed surfaces like this one. Here we have irregular bed surface, so these are the ripple formation. And this type of second type of resistance offered for due to drag, which is created by ripples in the bed. The pressure on the upstream side of the ripple, there are two sides of the ripple, upstream and where we have higher pressure, and the lower part where we have a little bit pressure. So this slope providing the necessary energy to overcome the resistance. The slope which provides the necessary energy to the flow, and that overcome the resistance of the soil, and it can be divided into two portions according to the above concept, using value of unquoted from different sources, from experience or from experiment for various conditions. And Lacy calculated that shock as measured in terms of slope represented more than 40% of the energy consumed by irregularities. For example, if flow is offering 100% energy, then 40% energy is consumed due to shocks. by the irregularities of the bed and the banks, and showing that more energy is dissipated in a channel with shock than without it. And he calculated used the same equation, and he further developed the two different types of factors. And what are the factors? Like he used F is equal to Km 1 by 2. K is a coherent factor, M mean diameter of bedside particle in millimeter. And second is Fr is equal to F into Fq under root. Fr silt factor in channel which is free from shock, which is free from irregularities, and F silt factor is obtained from the previous equation which we have used, and Fq silt obtained from stage discharge relationships. And here we have channel condition, and here we have values of N, and we can use this equation. And here it is derived simply that S is equal to slope for shock losses is equal to 43%, 43.7% of the total slope. This is capital S. This means that for a poor channel, 43.7% of the gross slope mean to say 43.7% energy is accounted by the shock, and 56% is available for the flow to overcome the friction and continue the surface water. And the second contribution is Blanch contribution. Blanch simply divided the frictional resistance simple F into two components, bed friction and side friction. FB a bed silt factor and Fs a side silt factor. He basically explained that the lacy silt factor, which is F, which was previously used F, that was constant for bed and side slope. He explained that these two can be used separately, as there are two different phenomena which occurs on bed and side slope. So FB is equal to V square over D, and Fs is equal to V cube over B. And what are here D and B? These are the mean depth and mean width. You can say that in our previous area calculation of trapezoidal channel, we used By plus Zy square, and in that equation B was bottom width, and but here B is the mean width. Mean width mean that is average of bottom width and top width. So here we have D and B. You can calculate the area by simply multiplying B and D, these two factors. Area is equal to D multiplied by B, because these are mean values, mean depth and mean width. So there is no need of side slope here. And the second equation for B is equal to, here you can see the cross sectional area can be calculated as B and D. And second equation for B and D is separately FB over Fs into Q, and this one. In defining F, Lacy did not take into account consideration of silt load being transported, but made it dependent upon the silt size only. But Blanch contributed it in a separate way, and he also introduced the bed factor is equal to that is a function of D. D means silt size in inches, and C is a silt concentration in part per million. So simply F is 0.123 for bank material, very slight, medium and high cohesiveness respectively. Cohesiveness mean that is near to clay. There may be high cohesive forces. And you can see the S equation, and in this equation there we have kinematic viscosity of water. It is almost equal to 0.98 into 10 raised to power minus 6. And the third one approach is Simons and Albertson approach. They published their results and analysis in 1960. According to them, major disadvantage of regime theory is there were three major disadvantages, like it has not been so developed as to be based on wide variety of conditions, and second, it failed to recognize the important influence of sediment charge on design, and third one is it involved the factor that require a knowledge of condition on which the formulae are based. So they basically introduced a new concept in order to overcome the above deficiencies. They collected the field data from 24 stable reaches of various canals situated in the Punjab and Sindh in Pakistan, and in USA the data included the whole range of conditions, like and they considered magnitude of discharge, velocity distribution, slope of water surface, slope of the shape of the cross section, sediment transport, total sediment load, samples of bed material, and other factors also. Even they introduce water temperature in order to calculate, because temperature has effect of kinematic viscosity of water. And they basically divided the conditions based on 5 types of channels. First channel, sandy bed and banks. Both bed and bank are of sandy material, and sandy bed and cohesive banks, clay type of banks, cohesive bed and banks, coarse non-cohesive material, and sand bed and cohesive banks with heavy sediment, 2000 to 800 parts per million of water. And they basically introduce the equation with respect to R, hydraulic radius, and there is a relation of B with respect to wetted perimeter, B with respect to capital B, D with respect to R with respect to condition of R less than equal to 7 and greater than 7 feet. And they introduce this equation, these 3 equations and 4 equations, and here we have channel types. Channel 1, 2, 3, 4 and 5. These 1, 2, 3, 4, 5s are this one. These are the channel types, and they introduce the value of coefficients K1, K2, K3, K4 and M, which can be used here. K1 for P, K2 for R, and K3 for velocity, and K4 for CG and slope. C and slope. So we can solve, we can understand these approaches with help of numerical. Example 4.4, we will solve this example with the help of all the approaches which are used. Design an irrigation channel to carry 60 cubic of discharge, sediment size 0.0125 inch and sediment concentration 200 parts per million, average water temperature 74 degree Fahrenheit and kinematic viscosity 1 into 10 to the minus 5, and banks cohesive and bed sandy. Sandy bed and cohesive banks. So this is, I hope so, case number 2. Sandy bed and cohesive banks, this is case number 2. Channel type of 2. So we will use these types of values in this approach. So it is first used by using Blanch approach. So I have also opened the similar book in another, so that we can be able to see the formula side by side. So in the first approach we will use the Blanch method. This is the data, and in Blanch method we have equation FB and FS. These will be calculated separately. We will calculate B and simple D, and we will use this D and this small b to multiply with each other to calculate area. So Fs is equal to 0.3, that will be used for highly cohesive banks. It will be taken from literature. FB, for FB we will use the equation like this one. D, we will enter D in inches and C in part per million. So particle size is 0.125 inch, so we will FB will be equal to 3.7, say 4.0, and then we will use equation of B, this one, and this one is equal to FB or FS into Q. We will use this equation, and B is average breadth. It is equal to 28 feet, and then capital D that will be calculated using this equation. These two equations will be used to calculate capital D. So D will be equal to 1.04 feet and B is equal to 28 feet. We will use equation of S. Slope is this, area is 29 point something, and side slope, then you can calculate area is simply B and D. Then you can calculate the other parameters. If you add the side slope, then you can calculate the bottom width 26 feet, that is less than 28, that is okay. Then you will calculate the freeboard, And the second approach, that is Simon and Albertson approach, and we will see this approach. This is the approach, and these are the equations of Simon and Albertson equation. And first of all we will calculate P using equation, this one. We have Q, we will enter and we will find P, then equation 4.28, then equation 4.28, this equation, and then we will calculate the other parameters. B is equal to 0.9 into 20.0, that is equal to B, and from equation we will calculate the capital B. From this equation we will put small b and we will calculate capital B, and B comma surface width, that is equal to 22.6 feet, that is the surface width, not bottom width. And from equation 4.32, this equation we will calculate R, and our channel type is 2, we will use K2 as 0.44, and discharge we will calculate R. So K2 0.44, discharge we will calculate R, and equation 4.30a, using criteria of R we will use equation 4.30a. R is less than 7 feet, then we will use this equation. D is equal 1.21 R, D is equal 1.21 R, that is capital D. Area is equal to B into D. B again simply from our B and D, this is equal to B, that is 18.18 feet, average width, and D average depth. Area from area 42 and area from PR, that is equal to 38. So area is more in this case, little bit less in this case. We can take mean of the area, that will be about 40, and we can calculate velocity. From velocity we can calculate slope, and from this equation we can calculate slope. Only this equation is enough, which is given in Simon and Albertson approach. This equation is enough, but we can use these two equations, and then we can make average of slope. We have every parameter except slope. Then slope can be average mean value of slope. Hence the channel is designed. Then you can add the freeboard also. In rational approach, the design of online channel by rational method is basically a problem of sediment transport. So any canal section will be stable if velocity, slope, cross section are such that all the sediment entering are swept away from the section, and clear water flowing through the canal does not scour the cross section. So sediment transport is a complex problem which may not be entirely amenable to rational analysis. Flow conditions are assumed to be steady and uniform, but actually it is not possible. Flow is always non-uniform and unsteady. So sediment transport is basically focused on bed load and suspended load. The bed load moves along the bottom of the channel and transmits its weight to static grains below. It moves forward by sliding or saltation or by jumping. Suspended load, it is a part of load which does not move in contact with the bottom. So there may be some interchange of grains, like some particles may be lifted up and some of the particles may be dropped back to the bed. So bed load functions, the first is of Debye's equation. It is one of the oldest method. He basically divided bed load. Bed is assumed to be moved in layer of thickness, like this thickness, equal thickness D, and the first layer, second and third layer, 4, and number of n layer, and the movement in upper layers will be more as compared to the lower layers. So Du Bois developed equation 4.35, where Q is basically the sediment in motion, that is equal to sediment volume per unit time per unit width of the bed, and the total thickness. And they further developed this equation, gamma ys, that is equal to gamma s minus gamma fs nd. Gamma s specific gravity, specific weight of sediment, fs coefficient of friction between sediment layer, and tractive force, T is the tractive force. And the critical condition exists when movement of the top layer is just to start. That the tractive force is called critical tractive force. That is equation 4.36. And if we compare these two equations, that if this is T and gamma ys, then T is equal to N into critical stress. You can use this equation here. Critical tractive force, Fs gamma s minus gamma d put here, and remaining will be N. So T will be equal to N into critical tractive force. N is equal to this, and another equation is this, that is equation of Qs. And we can also use equation this, where Q is basically the discharge per unit bed width. Small q is equal to capital Q divided by bed width, and Qs, that is here we have to enter Q and QC. Q actual discharge per foot width, and QC discharge of per foot width of channel with critical slope SC. And SC corresponds to tractive force C, that corresponds to this one. At this point, when critical tractive force, when movement of top layer is just started, then at that time tractive force is converted into critical tractive force, and slope is called as critical slope. And these are the values of CS and critical tractive force against the particle diameter, 1/8, 1/4, 1/2, 1, and so on. And particle diameter is in millimeter. And there are other equations which are similar to Du Bois function, Chung, Meyer-Peter, McDougall, and these are the equations for uniform sand and gravel, graded sand and uniform sand. And the second bed load function is Einstein bed load formula. Einstein basically provided the different concept as compared to Du Bois. He said a particle of a particular size moves in steps and definite length. Definite length means if one of the particle is lifted in the water, then after specific length, after for example 200 meter, 400 meter, it will be dropped back, and another particle will be lifted back. And frequency and rate of transport depends upon the number of particles moving at any time. If more number of particles are moving at any time, then their dropping frequency will be more and lifting frequency will be more. The probability of movement of any particle in a unit time, for example in 10 minutes, 5 minutes, is expressed with respect to rate of transport, that how many particles are being transported with the water, size of particle, immersed weight of particle, submerged weight of particle, and time factor. And third thing, this probability was also expressed in terms of ratio of dynamic forces exerted by the flow, because water exerts dynamic forces. Water try to erode the particles from bed and banks, and water also tries to keep the suspended particles in suspension. And there are other forces which are resisting forces, which are opposing the particle movement, that depends upon the cohesiveness of soil. And the two probabilities are other expressed probability 1, function 1 and function 2. These are related with the function, and probability 1 is also equal to this equation. Here Qs is volume rate of bed load movement per feet width per unit time. I mean to say kg per feet per second. And G is gravity, and rho is basically, and function 2, that is equal to rho is specific gravity of sediment, that is 2.4, that is almost 2.4. And GS is also equal to gamma rho QS in feet pound per feet per unit time. S is slope, and R dash is hydraulic mean radius that would exist in channel if bed were unrippled. And R dash is further, total R is equal to R dash into R double dash, and it corresponds to basically different components, that if bed was unrippled and bed was rippled. Basically, bed is usually rippled due to non-uniform flow and unsteady flow. The existence of R dash may be explained as follows. In a channel with bed ripples, it is assumed that total bed friction develops in two distinct ways. One along the sediment grains of the surface as a rough wall, and second by separation of flow from surface at characteristic points of ripples or bar. And usually we take R as one case. It is basically defined for two different cases. And here we have graph of Manning formula using Strickler's equation. And he introduced Einstein equation n dash is equal to 0.032 d1 by 6 and d is equal to d65. I hope so you have studied d65 in the basically soil mechanics course. So d65 mean 65% of the soil particles are finer than the given grain size, and this is the equation for relationship between function 1, probability 1 and probability 2. We can also use the graph and we can also use the equations. And the second amendment, which is made by C.V. Brown, has provided Einstein bed load function as function probability 1, and in probability 1 there is f. Use the f equation is here, and it is related with these two functions. This equation is basically, this graph is also being provided by C.V. Brown, which are amendment to Einstein bed load function, and we will solve this. We will use these equations when we will solve the numerical. And the third function is a suspended load function. For suspended load function, we have the equation like this one, and Ca concentration at any height y from bed, and concentration which is known at reference point at a height just above the bottom of the bed, and depth of flow, W fall velocity of grain, this is W, and K is von Karman universal coefficient, and V is shear velocity, that is equal to shear threshold shear stress divided by specific gravity of particle is equal to G ds under root, and intensity of shear stress at bed and density of water. So this row is density of water, and so now we will solve the examples of these equations. So Dubai's equation can be rewritten after the Einstein and C.V. Brown equation. Equation 4.44 is derived from Dubai's function. Equation 4.45 is also derived. This equation is also derived. Slope, critical slope equation is derived. 4.46, we will use this equation and this equation. So example 4.5, and we will solve this example using multiple equations as we studied. Design an online channel to carry a discharge of 60 cubic feet per second with a bed load of 100 parts per million. Mean diameter of bed material is 0.25 millimeter. Method 1, Dubai's equation. So we have to open Dubai's equation in this book, separate book, so that we can see the equations when we solve the numerical. And this is the Dubai's equation. These are the equations. So bed load is 100 parts per million. So 100 parts per million mean 100 into 10 to the power minus 6. So that is equal to QS over Q. QS is number of particles of soils, silt, and Q is discharge per unit width. So if that is given 100 parts per million, it means 100 parts of soil particles are there with million parts of basically per million parts of water. So QS over Q will be equal to 100 into 10 to the power minus 6. Y is depth of flow, we have to assume 2.5 feet. Then we have to use critical slope equation, that is equal to this one. So this is the critical slope equation which we use, that Dubai's equation can be rewritten. So this is SC equation we have to use. In SC equation, slope is 0.0001, assume n 0.0225, and using the equation 4.46 you can use this equation. And this equation. Qs over Q is equal to gamma square NY SDSCS, and from here we will calculate slope. It was critical slope when first particle starts to move, and this is simple slope, that is equal to 0.975 into 10 raised to power minus 3. 0.975 divided by 1000 feet, approximately 5 feet per mile. That is little bit higher slope. And then velocity equation, you can use this equation. We have every parameter, and then velocity equation, we will get velocity and from area and bed slope, and then you can calculate B, bed width, and then slope. This channel is design. Method 2, using Einstein bed load equation. So for Einstein bed load equation, and here we have Einstein bed load formula, and we have probability 1 and probability 2. So first of all, we have to calculate GS, and GS is equal to gamma rho QS. So here you have to make a little bit correction. Here 2.4, which is a specific gravity of sediment, that is missing from this equation. We already discussed 100 into 10 raised to power minus 6. Only this portion, 100 into 10 raised to power minus 6, that is equal to QS over Q. So here we have to enter only QS. Gamma is equal to 62.4, and rho, density specific gravity of sediment, that is equal to 2.4. You have to multiply it with 2.4, and this 60 over 10, 10 is width, assumed width, and 60 is discharge. 60 over 10, that is equal to small q, and this 100 into 10 raised to power minus 6, that is equal to QS over Q. So that is equal to QS over Q. We have multiplied with small q. So this is small q. Small, to cancel small q with small q, multiply by 62.4, multiply by 2.4, that will be equal to 8 point something into 10 raised to power minus 2 GS. So you have to put GS here in this equation, and you have to find the probability 1, and the probability 1, that will be equal to, and this equation is basically, this is the equation. This is the equation, and QS will be equal to GS over gamma into rho. GS over gamma into rho, that is equal to QS into this one. So you can see this value, that is equal to 2.4. This rho is specific gravity of sediment 2.4. You will find the function 1, that is equal to 13.20. So you have to move to the, and that graph is not, that graph can be found on the internet, like so this is the graph of sediment transport. This is Einstein bed load function. This is probability 1, and this is probability 2. So probability 1 is 13.20. So that graph is up to 10. So 13 will be after this, and from 13 you have to go to this graph line, and you have to go here. So at 13 this value will be about 0.8, 0.6 like this, and you can see this is 0.6. Then you have to use this function. This equation is here, equation 4.41, and you have to enter all the values, and you will find R dash into S. Then using this triangular equation, n dash is equal to this, you have to calculate, which is valid only for flat bed without ripples and represent granular roughness. So D is 0.25, and you have to calculate n. It is in millimeter, but you have to, here you have to enter into D65. So this is D65, and Material is non-uniform and no gradation curve is given, therefore D65 may be assumed as 0.6, 0.4. If a material may be uniform and any curve is given, then we can find out D65, but it will be given at 0.4 millimeter, 0.04, then divided by, it is divided by 30. It is millimeter, it is in centimeter, and divided by 30.48 to convert it into feet. So next, n dash is equal to 0.012. You have to enter n dash here, and then you will find an equation of R and S. So there is an VRS, there is another equation, R dash is equal to n dash over n into R. Here you will calculate R dash with respect to R. Here we will have RS with respect to V. Here we will have R dash S. So we have three equations and we have almost 4 parameters. So from equation 1, from this equation R dash S, RS, we have R dash in term of R. So you have to calculate R is equal to R dash over 0.386. So you have to enter in this equation R over 0.386, and it will be used here from equation 1. You have to enter value of R dash here to convert it into RS. Now we have this equation second, and we have total 3 equations and 3 unknown. So R dash RS is equal to 0.00578. Next we have Q, equation of Q, and we have to assume one parameter because we have 2 equations and 3 unknown parameters. One parameter R, second parameter S, and third parameter is velocity. We know Q, so we have to assume one parameter. It is as here we are assuming wetted parameter 16 feet. Then we can enter wetted parameter here, and we can find another equation in term of R and S. Now we have 3 equations and we have RS 2 equations and 2 unknown in term of RS. Put R from this equation in here and you can calculate S, and you can calculate R, then side slope, then you can select the depth, you can find the depth, and therefore Einstein bed load function gives these parameters of the channel. And the problem can be solved with Einstein and C.B. Brown plot that is given in the same book. Here we have plot of Einstein and C.B. Brown, Einstein-Brown equation. So we have equation 1, this one, equation 2, and equation 3. We have 3 equations, and we can also use the plot, but we will use equations. So by using this, we have to go to its formula. We have to calculate capital F. It needs kinematic viscosity, specific density of water. I think it is density of water or specific gravity. And we have to find theta. It is equal to, we have to find F, and F is equal to this one. So that is density, specific gravity of solid. This is not density of water. This is 2.64. So this is 2.64. We have kinematic viscosity, we have G, we have D. So we have we can calculate F, and every parameter is given here. G is 32.2, and D cube is equal to this one, and 1.64, that is equal to rho minus 1. So F will be calculated from here, and so D is basically grain diameter in feet. So you have to enter the grain diameter into feet, and after calculation of F, we have to enter F here. We have to calculate all the other parameters. We will calculate theta, and if theta is 28.8, we have to enter here. So theta is 0.458. We have to enter theta in this equation of phi. So equation of phi here, we have equation of phi as here, like here. Phi is equal to qs divided by all the parameters and f. So this is not theta, this is f, 0.458, and if we exclude this f, then this equation excluding f, it is equal to probability 1 in our previous numeric, in our previous example. So this is probability 1, this one. So that was equal to 13.20. I can show you that I am talking about this one. If we add f here, then this probability 1 is converted into theta. So probability 1 can be calculated by using this equation. So this is theta, 0.458 is f, put f here, all the values here, it will be resulted in 13.2, and it will be equal to 28.8. Then you have to enter in this equation, and this equation is provided in graph, this one. Then you can find the probability 2. When we have probability 2, then we can use RS equation. This equation we have derived in our previous case, like here, like in Einstein bed load function, we have calculated RS like here. The similar equation is there, and after RS we will assume P, again 16 feet. Then we will use another equation, like this case all the calculation will be similar as we did previously, and then all the parameters can be calculated. Then next is design methodology based on maximum permissible velocity, and the values in the above here, all the cases are reserved for well seasoned channel like this. But the design on maximum permissible velocity will help us to design a non-scoring channel. So its design procedure is simple. This is Einstein's, this is estimate n, side slope z, and maximum permissible velocity from the table. And then this is the table. This is the clear water and this is the silt water velocity, and T naught against the soil types. And then we have to use the side slope as given, and then we have to use Manning equation, calculate R, and continuity equation, weighted parameter, and basic equations to find out all the other parameters. I hope so these equations are now make very good understanding to all of you, and we will solve this numerical. Design an online channel to carry a discharge of 60 cubic with a sediment load of 100 ppm. Mean diameter of bed material is 0.25, and nature of silt is non-cohesive. Slope of ground is 1/1000. Nature of silt is non-cohesive soil. So average particle diameter of non-cohesive soil is 0.25 millimeter, is classified as fine sand, for which n and velocity are 1.5 and 0.02. 1.5 and 0.02. So fine sand 1.5 and 0.02. because 100 ppm is not a good amount of not a huge amount of sediment. So using continuity equation, we have V is equal to 1.49 over N, it is basically 0.02, and so on. We have to calculate R as slope is given, then from R we have to calculate area, discharge over velocity area. From A over R we have to calculate P, then all the other parameters we can calculate the channel section. But you can see in our first approach Y is equal to 0.5 feet and B is 79 feet. That is not a suitable channel with a width of 79 feet and depth of 0.5 feet. Then we have to change our design. Obviously the section with depth 0.5 feet and width 79 feet is not practicable because depth of 6 inches is very small and with a width of 80 feet almost. Therefore we have to change our design little bit. We have to now fix a depth of 2 feet. By fixing a depth of 2 feet using all the other values, it will give us a width of 18 feet. And then from P we have to calculate P using equation, and then R, then velocity, then we have to calculate area. Now its velocity is 3.06. By fixing the depth, if we fix the depth 2 feet, it gives us the width of 18 feet as compared to our previous case. So in this case velocity exceeds 3.06. Then what we have to do, it will be seen that for a depth of 2 feet and bed width of 18 feet as we did here, the velocity expected would be 3.06, which exceeds the maximum permissible velocity. So try another depth 1.5 feet and with a z of 1.5, and we can calculate B, that is equal to 23.6 feet. P, R and V is equal to 2.9 feet. Since the velocity is the criterion for maximum permissible velocity, therefore try another section. Now Z is equal to 2. We have increased Z. Here Z was 1.5 and here we have increased Z by 1.5 and B is equal to 23.6. Here B was also 23.6. And then we have calculated velocity 2.8, a very minor difference from 2.9 to 2.8 with an increase of 2 side slope of 2 as compared to 1.5. Now this also violates the maximum permissible velocity, therefore let us assume the velocity of 2 feet per second. Now we are exceeding the velocity little bit from 1.5, which is permissible, up to 2. Because in all the three cases the velocity is 2.8, 2.9 and 3.06. Now we are exceeding a velocity little bit, which is near to permissible velocity, in order to make a suitable design. If we fix the velocity, then we can revise the design in as we did previously. We have to calculate all the parameters. Now the channel section is Y 0.83 feet and B 34.48. It is acceptable, but little bit changes can be done. If we increase the velocity from 2 to 2.2 feet, then depth will be little bit more and width will be little bit less. Because one of the most important thing here at our first trial, when we had width of 79 feet and depth of 0.5 feet, this is not an economical design. Can you visualize in your mind that a channel with a width of 80 feet and depth of water in that channel 0.5 feet, it is not practically possible. So our target in this maximum permissible velocity design was to increase the depth little bit and to decrease the bed width in order to decrease the total economic excavation and canal cost. Next is design based on tractive force method. Similar to the design method evolved in Indo-Pakistan subcontinent, this methodology is also being practiced and observed. By definition, the tractive force is the force acting due to flowing water on the particles in order to erode the particles and to lift the particles which are already in suspension form. Composing the perimeter of the channel, it is a force exerted over a certain area and not on a single particle. So tractive force method basically focuses on a complete area, complete channel cross section, instead of a single particle. The permissible attractive force is the maximum unit attractive force that will not cause serious erosion of the material forming the channel bed and the banks. And this is the critical attractive force. If the flowing water will have more attractive force as compared to critical attractive force, then erosion from the bed and the banks will be started. So attractive force is equal to gamma ALS. So A and length. A is cross sectional area, length is length of the control volume. So AL represents that this attractive force method is based on the channel cross section. I mean to say bed and the banks, and it does not focus on single parameter particles. L is length of control, S is slope of the channel bed, and this is the unit attractive force gamma ALS over P into L. Now P is wetted perimeter, L is the length, and another equation that is equal to gamma YS. So this will be equal to, this will be resulted in gamma YS, and another equation is, so we will use this graph in our numerical, and there are other parameters like angle of repose and angle of side slope. We will use this equation 4.48 and 4.49 equation, and this is angle of repose of non-cohesive material. If it is not given, then we can find from this one. Now what is angle of repose? We have to see it from here. So this is the angle of repose. You have to put the soil sample on ground, and then you have to measure the angle with respect to vertical, with respect to inclined surface of the soil and horizontal surface. That is angle of repose. Now design an unlined channel to carry a discharge of 60 cubic on a ground having an average slope of this. Average particle size of channel material is this, and non-cohesive type. Value of N 0.02 for non-cohesive sand, and value of angle of repose of for a size 0.25 mm is not available here, but it will be assumed as 40 degree for non-cohesive soil. And assume side slope angle and B over Y. We have to assume B over Y. In this case, B over Y is equal to 4, and maximum attractive force on side particle, that is equal to 0.75 gamma YS, and this is basically this is gamma YS. So that is basically 0.76. We can use 0.75 or 0.76, and 0.75 gamma YS, attractive force ratio K. So K will be used from the equation like K will be used from this equation. K is equal to TS over TL, that is equal to cos beta 1 minus tan square beta over 1 minus over tan square alpha. So K is equal to this one, TS over TL, that is equal to 1 minus sin square beta over sin square alpha. That is also equation for K like here, and beta and alpha are the angles. Beta is equal to angle of side slope, alpha is basically angle of repose, K is equal to 0.876, and estimate, we have to estimate permissible attractive force on bottom, figure 4.10 for particle diameter, this with high sediment in water. Now we have to move to figure 4.10. So that is figure 4.10. For our case it is basically, so we have to see recommended values for canal with high content of fine sediment. 0.25 mm will be here, and we have to go to this number 2. This is number 2, and then we have to go here. We will have answer 0.06 or 0.07, but it is calculated at 0.085. Its unit is pound per square feet and pound per feet. So we have to calculate y ts over tl is equal to k. Ts is equal, so this was tl. Ts is equal to ktl, and ts is equal to 0.75 gamma ys, like this one. And simple t was gamma ys. Ts is equal to and ts is the critical force on side, and tl critical force on bed, and this was the maximum tractive force which we calculated from the graph that was on permissible unit tractive force on bed, tractive force for canal built in non-cohesive soil. Now ts over tl is equal to k. We can calculate ts, and unit tractive force for side was 0.75 gamma ys. Here it is written in the book, on this page number, on page number 163, it is written as that the permissible tractive force on the level bed of the channel is ys, and it will be gamma ys, while along the side it is 0.76. 25% less force is on the sides, and unit shear stress is unit tractive force gamma ys. So we can calculate ts. We can put values of 0.75 or 0.76. Gamma ys is equal to ktl. We have tl, we have s, we have gamma, we can calculate y, and b over y was assumed as 4. So b over y was 4. B can be calculated 6.8 feet. Now you can put all these values to calculate a, p, r, q, and q is again this equation, Manning equation, and then q is 28.8 cubic, but our discharge was 60 cubic, so we have to revise the design. So how we can revise the design? We have assumed these factors, 18 degree and b over y. We have to revise this value. We have to keep special focus on b over y. So we can prepare table. We had assumed b over y as 4. B over y was 4, and discharge was half, almost 28.8 cubic we calculated, but it was 60 in our numerical. So we started in this book started from 8, calculated y using this procedure. This was 8, and repeat the procedure, calculate y and calculate all the parameters and calculate q. Y, b, area, it is little bit less, it is 55 or 57. Keep it 8.25, it is 57. 8.8, so at 8.85 it is 59.36. that is a suitable design with 1.7 y and b 15 and so on. So this design is suitable. 8.85, the design is suitable. Now calculate all the other values like TL, like this one, TL, within, it should be within the limit. It should be 0.087, which is within the permissible limit. It is 0.087, but our calculated was 0.085. It is almost equal. And you can check the velocity. Velocity will prevent the sedimentation, deposition or silting, freeboard, then 1.64. Next is hydraulic design criteria, and we are going to skip the hydraulic design criteria, and we will use only one equation of this one, like VT. VT is volumetric sediment transport per unit width, square meter per second, volumetric sediment transport. And all the other functions like G, acceleration due to gravity, relative sediment density, and D50 representative particle size, Y depth of flow, bed slope, chassis coefficient, sediment density, water density. And the total sediment can be calculated by multiplying it with the width. Now another method is Munir and Qureshi method. This is the most research attempt in the design of online canal carrying sediment laden water. The authors have been based their results on laboratory flume experimental data. They have prepared ready to use nomographs and equations using numerical techniques. So sediment, they have calculated on two different criteria. One is sediment transport criteria, and the second one is the critical shear stress criteria. So the first one, which is sediment transport criteria. In the sediment transport criteria, we will use the equation and nomograph. Like this is the nomograph. This is the equation, probability 1 and probability 2. This is the equation and this is the graph. Instead of graph, we will prefer the simplified equation. And here we have bed load function. Probability 1, that is bed load function, that is related to Vt over gamma under root, gamma s, g, and so on, d50. And second one is entrainment function, that is equal to T naught unit tractive force, gamma s, gamma d50, and unit tractive force we already discussed is equal to gamma ys, gamma rs. In case of large channel, r is equal to y. Vt, bed load discharge by weight, kg per meter per second, and all the other parameters are here. So design procedure, given the sediment concentration of channel in ppm, we will calculate P, and then we will assume the B, and we will calculate it should be less than P. Compute the load Vt and determine bed load function from equation, and then determine entrainment function using bed load function, and then N, R, S, all the other values. So design a regime channel carrying 43 cubic discharge, which would bring with it silt charge of 0.323 silt charge millimeter average size, and sediment concentration is 50 ppm by weight. So sediment concentration is 50 ppm. It is now by weight. Assume N is equal to this side slope 1/2 ratio 1 specific weight of sediment gamma s 2.650, gamma 1000, and g 9.81. It is an SI system unit. Now starting the numerical from Lacey equation, this equation is little bit changed. Up to now it was 2.67 in FPS system, and now in SI system it is 4.75 Q. Q will be in cubic, and this will be multiplied. We will calculate P, that is 31.15 meter, and area is equal to P into R, 31.15 into R. Now we have to assume B, it is 27 meter. It should be less than P. Now first of all Vt. Now Vt is basically, you can see it is given as 50 ppm by weight. So 50 ppm by weight, now you have to multiply 50 with 43. Now we have to convert it into kg meter per second. Now you can see this conversion. This is part per million. We have to convert it into kilogram per liter. So you can see it is about 2, 4 and 6, 10 raised to power minus 6. It is almost 49.9. We can say it as 50. 50 into 10 raised to power minus 6 kilogram per liter. 50 millipart per million will be equal to 50 into 10 raised to power minus 6 kilogram per liter. So 50 into 10 raised to power minus 6 kilogram. Now it is in kilogram per liter. When we will multiply it with discharge 43 cubic, if it is 43 cubic meter per second, multiply it with 1000, it will be converted in liter per second. Liter per second. Now I repeat, it is 50 into 10 raised to power minus 6 kilogram per liter. When multiplied with discharge 43 into 1000 means this is now 43,000 liter per second. 43 cubic is equal to 43,000 liter per second, and liter will be cancelled with liter, it will be in kilogram per second. Now divide it with the width of the channel 27 meter, it will be kilogram per meter per second. Now it is 0.0796. That is volumetric transport rate. Now put Vt into this function, bed load function. We have gamma 1000, gamma s 2650, and all the other values. D50 we have G 9.81, we have D50. 0.323. It is in 0.323. It is in millimeter. We have to enter it in meter. Divided by 1000. It came because it is average size, D50 representative size. It is 1.286. And now you have to find the entrainment function from this one. It is given on the graph. Here we have entrainment function. This is the entrainment function. You have to put bat load here and you can find the theta, this one. So this is theta square, this is theta. You can find theta here, and you have to put theta here now, and gamma rs will be unknown. All the other parameters are known. So rs will be equal to 0.000431. Use Manning equation. You have a in term of r and r 2 by 3, and we had a is equal to 31.15. r put a here. R will be 5 by 3 into s 1 by 2. Here you will get another equation of r into s. Now we have two equations and two unknown. Put r from here, calculate r from here in term of s. Put here, you can calculate s and r individually, and from all the other parameters you can calculate along with the freeboard. Second one is the critical shear stress criteria. Munir and Qureshi also developed two more relationship between shear intensity factor and particle Reynolds number. The above equation help to design the Canal parameter which will generate the required critical shear stress on the bed and corresponding Reynolds number such that allowable discharge will be released into the canal for stable conditions. So we can use this equation, and we can use this equation. Its design procedure is, first of all, compute Munir parameter. The equation for Munir parameter is MP. This is the equation. D50 representative size. It is the I hope so, kinematic viscosity and all the other parameters. And second, read shear intensity factor for corresponding value from the graph, and we will compute hydraulic radius, determine velocity. So we will see how to design it on shear stress, critical shear stress criteria. Design a stable channel for the following given data: Q10 Qmac, D50 2.5 mm, gamma S 2700, Z2 S, G, and temperature. From temperature we can calculate kinematic viscosity. In this equation put temperature and you can calculate 1 into 10 to the power minus 6 square meter per second. Enter all the values in this equation including the kinematic viscosity. We can calculate Munir parameter MP. Now MP is 246. From figure 4.15 you have to calculate this factor. This is called dimensionless shear stress. So we have to go to the other criteria. This is figure 4.15. So this, on y-axis we have dimensionless critical shear stress, that is equal to this one. Critical shear stress over gamma S minus gamma into D50. Now we have Munir parameter 246. So from this graph we have Munir parameter. So this horizontal line represents Munir parameter value. It is 246. It will be here 100 to 300. Here will be 200. Here will be 246. From 246 you have to come parallel with this line, these lines. In this pattern you have to come on this line. For example, if here is 246, we have to come parallel to these lines up to this point, and then we have to go to y-axis. From this point we have to go to y-axis. Here will be value of dimensionless critical shear stress. Now it is 0.055. From this one we can relate it with the critical shear stress, that is equal to gamma RS, and RS will be come out. We have slope, yes, we have slope also, this one. So R will be directly calculated from this. And next, U over U steric is equal to this one. And what is basically U over U steric? So U over U steric, that equation is here, that is called resistance factor, that is related to R over D50, and U steric is equal to shear velocity GRS under root, and U is equal to mean velocity of the flow. It is the shear velocity, that is the mean velocity of the flow. And from this one we can calculate U over U steric. U steric is equal to GRS under root. We have now R, we have this one R, and we have every parameter. We can calculate U as, now it is 0.556 meter per second. You can see here D50 2.5 over 1000. 1000 is gamma, it is entered in millimeter here. And here parameter was 0.4 meter. You have to enter it in millimeter because it will be, I think it will be 2.5, I think. Little bit mistake is here, like it is 4.91, here it is 4.19, but it is 4.91. I think it will be 2.5, 0.4 into 1000, it will be millimeter, and so on. It is 0.556 meter per second. So you can calculate area, you can now calculate R and all the other parameters. Next step is canal lining. This canal lining topic will be assignment to all the students, but I will show little bit topics here, like canal lining is expensive business when it is unavoidable, when it is necessary, when the track of the land through which the canal is passing is highly pervious and seepage losses are more, when the loss of water through seepage is very high. In order to control the water logging, if there is water logging, the groundwater is very near to the water table. Water table is very high to the root zone. Then we have to line the canal for the defense purpose. When the canal is to serve as a line of defense, and the water should remain in that canal. And here we have advantages of canal lining. Types of canal lining, there are different types of canal lining, like clay puddle lining. Next we have these types of canals. For example, the first case, natural surface above full supply level. So you can see this is the full supply level. This is full supply level. This is the main canal boundary. This is bed width of canal. So here we have cross drainage structure, any other canal, and here we have road. Road surface is higher and water level is below. Natural surface above full supply level. Natural surface is above the full supply level. So this is the dash line. This dash line is of road, and that is higher than the water level. Second one is the natural surface level below full supply level but above bed level. Road is above the bed. This is the road level. Road is above the bed but below the full supply level. Here the embankment little bit will be more, but the third case, when road will be lower, will be equal to the bed, or the road is below the bed level, then we have to make higher bunds like dowel. This is dowel, this is higher height, and this is embankment. This will be the hydraulic grade line. So in our dam design, we will study this hydraulic grade line, that seepage, if water seeps, then it should not come on the road. It should not create any ponding, any surface runoff on the road. So we have to increase the embankment height and length in this case. You can see here we have less, here less, but here we have more in both the cases. So lining material, cement plaster and shotcrete lining and cement concrete lining. For example, the lining, here we have lining, and in between the lining or in between the tiles we have bitumen filling. So this is the brick lining. Let me explain this one topic. On the lower side we have, here you can read 12-inch, 6-inch and 2-inch tiles in 1:3 cement sand mortar. These tiles are prepared into 1:3 cement sand mortar, and dimensions length, width and height of block, this one block. So these are placed over this one. This is placed over this one. This is placed over this one. So second layer is 1/2 half-inch cement sand plaster over this one cement sand plaster, and then third one we have 1/8 inch asphalt membrane. This black line, this is laid over tiles, over this tile, that is same dimension, but its mortar is 1:6, 1 cement and 6 sand. So this one and this one, these tiles are prepared, and below the tile there is 1 inch thick 1:6 cement sand mortar. So at the bottom we have cement sand mortar 1/6, above we have tiles made of 1:6 cement sand mortar with these dimension. Then we have asphalt membrane, then we have cement sand plaster 1/2 half inch, then we have tiles again but with a highly cemented like 1:3 cement sand mortar. This is the brick lining, and this is another lining. You can read it with the same principle. This layer over this one, this layer over this one, this layer over this one. So at below we have thick subgrade of 1 cement mortar 1:10, and then thick cement mortar over this one. Then we have tile, this one 1:6, then we have cement plaster, this one, then we have thick cement mortar over this one, and then we have tiles. And the next and the last topic is method based on discharge capacity of irrigation canals. So before starting this one, we have to understand one important thing, that the last method is based on consumptive use. So this is the equation that is basically used as a demand based system, that how much the demand is there for designing a canal. Q is equal to quantity of water required by crop in acre feet, that is volume, at outlet per 1000 acre of CCA. So that is acre feet, I mean to say Q is volume for 1000 acre. So CF crop coefficient, E lake evaporation or pan evaporation, R is effective rainfall, I is cropping intensity, E is farm efficiency, and S is soil moisture depletion in inches, P is pre-irrigation in inches. You have to enter all these values here and you have to find out the Q. So before the canal designing, in our all the numericals Q was given, but here we can calculate the Q. Then this small q will be used to find out the total Q. Small q is in acre feet. For n number of days we can calculate capital Q, that is equal to 4840 into 9 over n into 24 into this. This is for total quantity of water required at outlet per 1000 acre of CCA during given time period for n number of days. For example, if you want to get water for 10 days, for 9 days, for 7 days, you can put n here and you can calculate the all the other factors. So we will design a canal of these tables are correlated with the canal design in our last design, but we have to study little bit theory. Irrigation department method, for example, we have to familiar with the full supply factor. This is called duty. One term is called duty, one term is called as delta. Delta mean total water required for a crop from sowing to harvesting. For example, wheat requires about 17 inch, rice require about 48 or 45 inch of water. So duty means area over discharge. This means duty of the canal, which is the design stage. The word duty means the area successfully irrigated during a base period per cubic of average supply. I mean to say full supply factor is equal to duty, that is equal to area over discharge. Base period is the period from first irrigation to last irrigation, and crop period is the period from sowing to harvesting. This is the difference between base period and the crop period. So second one is intensity of irrigation. This is the percentage of cultivated area. For example, if we have 180,000 acre, from 80,000 acre, if we have 80% 80% cultivated area, then 80 multiplied by 0.8, 64,000 acre will be cultivated. And if we can say 50% is irrigated, so irrigation intensity is related to percentage of cultivated irrigable area irrigated during a given period. So 64,000 into 0.5, 32,000 acre will be irrigated area. The entire cultivated area is not generally expected to be irrigated. So irrigation intensity is fixed separately for kharif crop and rabi crop. Theoretically, a maximum intensity of 200% can be there. For example, if a farmer has 20 acre and he irrigate 20 acre in kharif and 20 acre in rabi, so in a year he irrigated 40 acre, 20 acre in kharif, 20 acre in rabi, so he irrigated 40 acre from his 20 acre. So its cropping intensity will be 40 divided by 20. 40 mean net sown area, 20 mean its total area. 40 over 20 will be equal to 2. Multiply with 100, that will be equal to 200%. But practically in Pakistan, the irrigation intensity is about 180-170% due to shortage of water, rest of land. Some farmer give rest to their land after some years, some season, danger of water logging. And kharif rabi ratio, kharif crops required more water and rabi crop required less water. So this ratio is also very important. And the last thing is water allowance. That is very technical term. Usually that is asked in an interview. That is total cusick required at an outlet for 1000 acre. Total cusick required for 1000 acre. For example, if we discuss about the Punjab, in Faisalabad it is about 2.5 to 3 cusick per 1000 acre. If we go to Janubi Punjab like Muzaffargarh, Bahawalpur, it is 5 to 6 cusick per 1000 acre. If we go to lower Sindh areas, it is about 12 cusick for 1000 acre. So in upper Punjab it is less. It is in Janubi Punjab more water is allowed to the farmer. In Sindh even double or triple water is allowed to the farmer. In Balochistan I think its value is 1.5 to 2.5 cusick for 1000 acre. So its procedure is very simple. We will solve its procedure with a numerical. The kharif duty for an area similar to the project is 80 acre per cusick. A project is working and kharif duty is 80 acre per cusick on the basis of factor influence the duty. And full supply factor duty is 60 acre per cusick. Determine discharge capacity of the canal system. Other data is provided below. Full supply factor that is duty 60 acre per cusick. Total irrigated, total area 1,08,000, unfit for irrigation 8,000. So remaining cultivated area will be 1 lakh acre. Irrigation intensity 80%. It means from 1 lakh 80% is irrigated. 80,000 acre will be irrigated. And kharif rabi ratio 1:1. It means 40,000 acre will be irrigated in kharif and 40,000 will be irrigated in rabi. And discharge required at the canal head, we have 40,000 acre area and we have 60 acre per cusick. So divide it, it will be 666.6 cusick is available. So absorption losses may be accounted for 10%, 66. So exclude 66 from 666, it will be resulted in 600 cusick, and we assume water allowance of 6 cusick. And it will be used as, for example, if canal is going to be constructed in Janubi Punjab, Muzaffargarh, you have to use that water allowance. If it is being constructed in Upper Punjab, you have to take that water allowance. And it is given in table. In our last lecture, I shared a book, Applied Irrigation Engineering. In one of the chapters, the water allowance is given. You have to just search the water allowance in that PDF file and you will get the values. And I will also share again when we will study. Now, these are the column numbers 1 to 8. So these are column number 1 to 7, 8 and 9. So these are the column numbers. So column 1, we will start from here, and let me rotate the screen. So column number 1, that is equal to serial number. Column number 2, reduce distance of an outlet. So for example, the canal there are multiple outlets which are off taking from that canal. The first outlet is at 1200 feet on left side. The second outlet is at 3250 on left side and 3250 on right side. At this point, only at 1200 feet from canal head, reduced distance. Reduced distance means the distance from where the canal is off taking. So this 1200 feet is from the canal is off taking up to the outlet number 1, and this is the distance again. And here we have two, one on left side and one on right side. Then we have one on left side, then we have one on right side, then we have two, one on right and one on left, then we have two again, one on left and one on right. It is again 1600, 450, and then we have 20,000, the last one, that is of 20,000. So I would like to share this one with you, the map. So you have to remember first four. For example, so you have to remember the first four, like this map. So this is the reduced distance, that is 0, canal is off taking, and the first outlet is here, that is at 1200 feet, and it is on left side. Then we have another outlet which is at this point. Here we have one right side and one we have left side, and their distance is given here, 0, 1000, 200, 3000. So our first was at 1200, second one was at 3200, I think. So first was at 1200, then 3200, then 5000 and 7800. Then third one is this one. This one is on one side, I think left side. This is at 5000. Then 7800. This is the 7000, and here will be 7800. And we have again one on only right side. Then we have again two, right and left side. These were on 12,000. And then when we have only two, again 16,000 at 16,000 feet. And then at the end we had only left side, like this one. At the end we had again left side at 20,000. So this is the design. From here the canal off takes, and water goes, and here we have one outlet, here we have two outlet, here we have again one outlet and one outlet. So this is dash line, you can see this is the hydraulic grade line. I hope so you have discussed and you have studied in our outlet chapter its calculation. If you feel any difficulty, then we will also discuss chapter 8 again. This is the formation of hydraulic grade line, and you have to calculate hydraulic grade line using the numerical which we studied in our chapter 8 outlet. So now we have to design the discharge and losses at each of the section. So you have to just focus on the table, like here. On first outlet, the data was, this is the given table. You have to work from here. There was area 450 and 150 was uncommanded, ghair mumkin. It is written in Urdu, uncommanded area. So from 450, 150 will be subtracted, and it will be resulted in 300. That will be irrigated. So second one is 725, 125 is uncommanded, then 600 will be irrigated. So these are the irrigated areas. So column 6 is obtained from column 4 minus column 5, 4 minus 5, and 7 we have to calculate with respect to 6 cubic per 1000 acre. For example, it is written as 300 acre. So we have 6 cubic for 1000 acre. So you have to multiply 6 multiplied by 300 divided by 1000, you will get 1.8. Next 600, you have to multiply 600 with 6 cubic per 1000 acre. 600 multiplied by 6 divided by 1000. Third one, 900 multiplied by 6 divided by 1000, you will get 5.4. And these are the discharge which are required at the outlet. So this is the total discharge. Again, it is written as same. So next we will work on this table. Now from downstream to upstream, when you have to design a canal, you have to work from tail to head. At tail we have a distance of 20,000. We have one outlet at left side, and that is requiring 8.4 cubic. We have at 20,000 left side we have one outlet, only one. All other are different. On 20,000 we have only one left side, and it is requiring 8.4. So similarly you have to rewrite this in reverse order against this column. So this is written as this one, left right and so on, and this one. So at this point we had only one on left side, so it is written as 8.4. You have to write on the next. This 8.4 should be allocated to this one after this one. For example, in other simple way, if water is passing a distance of 16,450, then there should be a water of about 8.4 cubic in the canal in order to meet the demand of next. Okay, it is 8.4. Remember, I want to explain this. For example, if water in this canal is passing this point is 1600 and 16,000 and something. I mean to say this point 16,450. If water is coming from head to tail in this way, head to tail, and water is passing 16,400 feet distance, I mean to say if water is passing by these two outlets and going to this one, the amount of water in the canal should be 8.4 in order to meet its requirement. So when water is passing this one, so there should be enough water to meet the demand of this right, this left, and this left one. So this table is written as, when water will be at this point, it should be 8.4 after this one. You can read it here, total draw of take in reach. At this point we should have 8.41. So this is the same distance, 7.8 and 8.34. You have to add, it is 16.74. Now 16.74 and 8.4, it will be about 25 point something. Now if water is passing this point, there should be 28 point something water, 16 for this, 8 point something for this. So this is written in this way. And third one, we have only one right and one left, again same. Then only one at 78,000, only one at right, it is 6.48 written here. Then again 5,000, only one on left side, 1.2, it is written here. Then again 2, 3250, 3250, one on right, one on left, 5 and 3.6, 8 point something, like this we have to write here. and 8.6, and then 1.8 is here. So these are the absorption losses in canal, these are the absorption losses. So how to calculate the absorption losses? You have to calculate the absorption losses like this way. Lacy silt factor is 0.9, absorption losses QL is equal to Q sec per 1000 feet of channel length, that is equal to 0.013. You have to calculate these losses using this equation, 0.0133 length into Q. Length you have to enter this one. For example, if you are calculating absorption losses of this one, so 20,000 minus 16,450, this will be the length, about 3,650. This will be the length. You have to put length here, and you have to put the total discharge 8.4. It will give us 0.152. Similarly, you have to calculate the losses using this equation, and then total capacity, this one plus this one, this one plus this one, these will be the losses which should be there, which should be added. Then you have to accumulate this one, 8.55 plus this one, 25 plus 12, 37, 37 plus 6.44, 44 plus 1, 45, 45 plus 9, 55, 55 plus 1, and 56. So there should be 56 cubic discharge at the first outlet. At here we should have 56 cubic discharge, and then we should have 55, 45, 44. Here we should have 55, 45 and 44 and so on. At this we should have 8 point something at this point. At this point we should have 25 point something, like this one. Now you have to design. Now it is important step, last 3 column. Now you have to design each canal section with respect to this discharge. So this canal section will be designed on base of Lacy silt factor theory, and you have to design with any suitable method which we have studied. So you will use this discharge and you will design the canal. You have value of silt factor, and you have distance of that section. You have to assume the bed width, or you can do, but you have to design it by yourself by using any of the design method which we have studied in this video. You have to design this cross section, but here discharge is changed. This will be designed separately, this will be designed separately. So each canal section will be designed separately. So you can see the dimension. Let me discuss. At the head, at 1200 meter, canal have width 14.63 and depth 2.4, but discharge will be delivered to first outlet, second outlet, third outlet. The dimension of the canal will be narrower. So the canal will get narrower from head to tail. You can see the width 14 point something, 14, 13, 13, 11, 8 and 2.8, because discharge is less. So each section, each length in between these should be designed separately based on this discharge. So another term is, if discharge is more, slope is also more. You can see here. Discharge is more, I think slope is less, but dimensions are getting narrower from head to tail, and depth is there will be not so much difference in depth, but in dimension, in width. So you have to design the side slopes. Then you have to prepare this graph using numerical of chapter 8, in which hydraulic grade line was calculated. If it was not discussed, we will repeat it in order to see whenever we design a canal, we design it water surface level, freeboard, its hydraulic grade line. You have to design it using all the numericals which we have studied in this chapter. Next questions, you have to just go through these questions. If you feel something different or something new in these questions, then we will discuss. So this was our chapter number 4 of canal design. Only one thing which I skipped in this chapter, that was hydraulic design criteria. It involves it because it is not practically being employed in Pakistan. It is not in applied form. It is, I think, hydraulic design criteria. It is here, but this was the equation for VT. What we get. So this was the hydraulic design criteria. It's there is no numerical of this design here, so I just skipped this one.